probability. So the probability of event A occurring given that event B has occurred is denoted by probability A given B. Okay, that's a simple probability A given B. That's what you're trying to find, which reads as the probability of A given B. So, okay, event A, probability of event A occurring and telling you that some other events already happened. Okay, we've written that as A given B. So what is probability A given B like expanded? Like if we expand that, how we can calculate that is the probability A intersects B over the probability B. So over the given probability. Okay, over the probability B. Probability A intersects B. B given A will be probability A intersects B over probability of A. I just have some question. Let's say probability A and probability A given B. Which one do you think it will be larger chance? The front one or the second? The first and second?
It's a second question, you say.
Same condition, like all same condition. Well, let's have a think. B got some connections with A and already let you know that B is happening. Okay, that will, think about it, it will increase the probability of A, like the chance of A happening. Not necessary, but most of the time will increase the probability of A happening. We'll see some examples later and you will come back to think about this question. Not 100% sure, okay, not 100% sure, but like most of the time will increase the probability. Anyone hold that? Okay, and let's have a think about this probability, like that's the formula, okay, that's the formula. And then let's have a think, what is probability A intersects B? What's the probability of A intersects B? So probability A intersects B is the number of A intersects B over the number of total. Okay, if it's countable event, like I can say how many things in the set, how many things in the intersection, we can go for number. And similarly, what's the probability of B? Probability of B will be number of B over the number of total. Okay, number of B over the number of total. Okay, and number, like let's see, we can times number of total on both top and bottom. Then what has been left is number of A intersects B over the number of B. Okay, number of A intersects B over the number of B. Okay. This is only true when the event is countable. Okay, you can count how many events are there in the set. Like later, like in year 12, you will learn continuous events. You can't use this formula anymore because there's no, like you can't count them. Okay, there's no number in them. You use only this formula is always true. Okay, what you have in the box is always true. So you can always use that formula. That formula is true for all the probability questions, but the back one for this one is only for discrete or say countable events. Okay, only true here. And let's have a look. Probability A given B differs from the probability A in that the sample space is reduced to the set B. So what's the proportion? If you ask me what's the proportion, if the area is sketched in ratio, okay, in the correct ratio, so the probability A will be what we have here over the total rectangle. Okay, over the total rectangle. And A given B will be this red area over this total. Okay, over this total. Like the whole B circle. Okay, given you B happen, so all the events is reduced into this B. And then you want A happen at the same time. It's the intersection part. The intersection is A happen and B happen. So over the B of the total. So over that thing. So the previous question, ask you to say probability A and probability A given B, which one is larger, which one is smaller, it's actually can't really tell. Okay, you can't really tell. It's like two different proportions. It's not over the same total area. So let's say in this case might be probability A given B is bigger. But if I can sketch another case, okay, I have a really big A, okay, and I have a quite big B. But this ratio is actually smaller. Okay, the intersection part is very little. So the probability A given B not necessary to be that large. Okay, so it's hard to say. Okay, and there's a formula. Okay, this formula is called the law of total probability. Okay, the law of the total probability. Well, I can say that can be easily done by tree diagram, but it's better to know this law. Okay, it's better to know this law. It's basically a tree diagram. So probability A, what is probability A? Probability A will be probability A given B times probability B plus probability A given B dash times probability B dash. Okay, you'll see the examples later of using this. And I can also show you how you can use tree diagram to do that question. So this formula, you need to know this formula. Okay, it's better to know this formula, but not necessary to use it unless it's asking you use the law of total probability. Then you come back to use this formula. Okay, example 1. In Stephen's class, 12 students study Chinese and 20 students study French and 8 students study both Chinese and French. Given that a student, okay, can you see the word given? Okay, the word given, knowing that, or something like that. Those two are the appears a lot. So it shows you that it's a given condition. Okay, that tells you something already happened. So knowing that or given something. There will be other ways to talk about given questions, but there's not as often as those two appear. So I can't really write all the things down for you, but you will understand. If it talks about something already happened, if it's telling you that something already here, that is a given condition. Okay, that is a given condition. So given that a student in his class studied Chinese, okay, so study Chinese is something already happened. So I want to know the probability. So I want to find some probability. What is the probability I'm trying to find? What is the probability that also study French? So French must be the thing you want to find. And given that this kid studied Chinese already. Okay, so that is F given C is part A. So that is number of F intersect C of number of C. So number of intersection will be 8. And number of students studying Chinese will be 12. And 2/3. Okay, 2/3. And part B says, given that a student in his class studying French, okay, studying French already, what is the probability that they also study Chinese? So now I want to find the probability of studying Chinese. So what you're trying to find, you put that in the front. And given, so what already known at the back? So C given F. So it's the number of C intersects F. So number of intersections over the number of F. So 8 over 20. 2 on 5. Okay, 2 on 5. Okay, example 2. In a certain town, the probability that it rains on any Monday is 0.21. So what you will know is the probability of raining on Monday will be 0.21. So we just write that into mathematical representation, what we already know. Okay, and also if. Okay, if is another word showing you that it's a given question. If something happened. Okay, if. Given knowing that if. So if it rains on Monday. So something already happens. Should be something already happened. Monday rains already. And then the probability that it rains on Tuesday is 0.83. So the probability Tuesday given Monday already rain is 0.83. If it does not rain on Monday, if it does not rain on Monday, okay, another if is another given condition, then the probability of rain on Tuesday is 0.3. So the probability rain on Tuesday, given that Monday dash not rain, is 0.3. What's the probability of M dash? You know probability M is 0.21. What's the probability M dash? 0.79. 1 minus 0.21. 0.79. Okay, so A, what A is asking? Yep. Well, you can always put in decimals. Like, well, if you can't express in, like, you can't really divide them, like say, 0.33 a third, you won't turn that into decimal. Yeah, generally leave as decimals. Generally, like, doesn't matter, it really doesn't matter. Well, we doesn't really put into percentage. Well, a quarter and 0.25 doesn't matter. Like, it's all the same. It's like not prefer or not prefer ones. But like if it's a third, we must leave as a third. Can't divide. Okay, A is asking both Monday and Tuesday will rain. So Monday rain and Tuesday rain. So it's asking the probability Monday intersects Tuesday. You should have the ability to use mathematical representation to show what is asking in the question. So this question is basically asking probability M intersects T. So what I should do? So first I need Monday rain, right? I need Monday rain. So Monday rain is 0.21. And I know in Monday rain. And I want Tuesday rain. So that will be times another 0.83. Okay, I want Tuesday rain. But Tuesday will rain with a chance of 0.83 because it's already rained yesterday. Okay, so 0.21 times 0.83. Okay, B. Will rain on Tuesday. Okay, here is the total, the law of total probability. What it's asking is probability of raining on Tuesday. So it's basically you find probability T. So if it's probability, so probability T will affect by whether it's raining on yesterday or not. So I can write that as probability T given M. Oh, too large. Okay, B. I'm asking probability T. So probability can be written as probability T given M times probability of M plus probability T given M dash times probability M dash. Okay, that's the total law of probability. A given B times probability B. A given B dash times the probability B dash, and add them. So Tuesday was affected by Monday. Then Tuesday given Monday rain times the probability of Monday rain plus Tuesday given Monday not rain and times the probability of Monday not rain. That will be the total law of probability. And what we have is 0.83 times 0.21 plus 0.3 times 0.79. And you can calculate that. Well, say if, let's say, we have a tree diagram. We have Monday rain, well, we have Tuesday rain, Tuesday not rain, Tuesday rain, Tuesday not rain, and we have Monday rain, Monday not rain. And if it's Monday rains, I have 0.21. Monday not rain, 0.79. And Monday rain, Tuesday rain will be 0.83. Monday not rain, Tuesday rain is 0.3. And therefore here must be 0.7 and this must be 0.17 because they add up to gives you 1. And then if it's Monday, Tuesday both rain, just times 0.21 times 0.21 times 0.83. If it's Tuesday rain will be this probability plus this probability and add them together. Okay, so it can be done by tree diagram directly. Or if you know the law of total probability, you would use that. Okay, that's the given event. Conditional, this is called conditional probability. Just before I start independent events, I want to ask you one thing. What is mutually exclusive events? What happens to intersection? No intersection. So mutually exclusive is no intersection. So mutually exclusive is no intersection. Okay, let's have a look what is independent events. Independent events are not affected by the previous events. Okay, independent events are not affected by the previous events. Okay. So basically what happens before doesn't have influence on what I'm going to do next. Example of independent events will be toss a fair coin twice. Okay, what's the result for the first one? Doesn't really influence what I will have for the next one. The chance will be the same for both events. Whether Lily will wear a red dress are independent of whether Jack will wear jeans tomorrow. Okay, what they will wear is totally independent. Okay, it's totally independent. So examples of dependent events. So what are dependent? Whether tomorrow will rain depends on whether today will rain or not. Okay, so the weather will get like today and tomorrow's weather is not independent. They depends on each other. Well, like Melbourne, it rains every day. Good example. I randomly choose candies from a bag without replacement. Again, the word is without replacement. If it's with replacement, that will be independent events. If it's with replacement, that will be independent events because I put it back, so the chance of getting the candy next time will be the same chance, like red candy is the same chance. But now without replacement, so what I have taken out for the first time will have an influence on my second choice. Okay, the probability will increase or decrease. So without replacement will be dependent events. Okay, now you have an idea of what is dependent and independent events. And I want to ask, like, okay, let's say I have a statement. The statement says that independent events are all mutually exclusive events. Is that correct or not? Independent events are all mutually exclusive events. No, have a think about it. And if I say mutually exclusive events are independent events, is that correct? Mutually exclusive are independent. Well, I think you must think about one must be yes, one must be no, right? That's not the case. Both not correct. Okay, both are not correct. So independent events and mutually exclusive events are completely two things. Completely two things. Okay, so, and to say 99% of the time, if it's mutually exclusive, it won't be independent. If it's independent, it won't be mutually exclusive. It's more like that. Okay, they're not having influence at all. Okay, and most of the time, then, like, if one happens, the other one won't happen. I'll show you in formula why this will be true. And let's say mutually exclusive gives you that the probability A intersects B equals to 0. Okay, probability A intersects B equals to 0. That's the mutually exclusive events. Okay. I will just give you an example. So let's say an independent event will be whether I will wear black or I will wear red will be independent of the weather. Okay, it's rain or like it's rainy or not. Like it not depends on the weather. Like it just depends on what I want to wear. But we can have intersections. Okay, if it's rainy, I can still wear red. If it's rainy, I can still wear black. Okay, if it's not rain, I can still wear red or black. There will be intersections for all of these four events. They are not mutually exclusive, but they are independent. Okay, there's no connections between each other. And let's have a look at the formula. Two formulas that can be checked whether the events are independent or not will be, first one, okay, if A and B are independent, then A given B will be the same as probability A. Okay, A given B will be the same as probability A. Why? Because there's no influence. Okay, there's no influence whether B happen or not. My A will always have the same chance of happening. Okay, so using that formula, okay, this is a formula like really makes sense, okay? That is the definition of independent events. If I can expand that, that's probability A intersects B over the probability B, and that equals to the probability A. Okay, that equal. If I can times probability B on both sides, that will give me probability A intersects B equals to probability A times probability B. So this one, I use the first equation to set up another one. Okay, this one is more often. Okay, we use that more often. This is really like the definition. Okay, this is more, the first one is more like the definition. And use the first one, we give the second one, and the second one will be more often used. Okay, we most of the time we'll use the second one to test it. Okay, for multiple events with selection made with replacement are independent. Okay, with replacement are independent. Without replacement are not independent. Okay, without replacement are not independent. So selection questions, it depends on whether you can replace it or not replace it. So let's say if A and B are independent, then probability A times probability A intersects probability B will equals to probability A times probability B. Okay, if we want them to be mutually exclusive as well, what do we need? We need probability A intersects B equals to 0. Okay, have a look at the two formula. So is either prob A equals to 0 or prob B equals to 0. Right? If I want the intersection to be 0, and already you know that the intersection will be A times B, then it's either A to be 0 or B to be the 0. It's not going to happen. Most of the time, it's not going to happen. If there are two events, how one of the events will be 0 chance of happening, which means there's no such event. Okay, so mutually exclusive and independent are not going to happen at the same time. Okay, like say 99% of the chance not going to happen at the same time. Well, it can't be the same happen at the same time. Well, A to be 0, B to be 0, like can't be independent then if you think about that way. Okay, if A is 0 or B is 0, it can't be independent. If there's no such event, why we talk about independent events? So those two things are not going to happen at the same time. Mutually exclusive are not independent, independent are not mutually exclusive. So that's proved by using the formula. Let's have a look at example 1. A selection of 10 mobile phone offers includes 4 free connections and 5 with a free second battery, while one offer has both free connections and a second battery. Let A be the mobile phone with free connections. Let B be the event of a free battery, a second battery. And draw the Venn diagram. So let's go for A and B. I have one in the middle. Okay, one got both. So event A is free connection. How many of them got free connection? 4 with free connection. So I will have 3 inside here. 5 with a second battery. So 4 will be here. How many phone in total? 10. That's 8. I have 2 outside. So probability A. So probability A will be number of A over number of total. So number of A will be 4 over number of total will be 10. That's 0.4 or 2.5. Probability of A given B. Okay, probability of A given B. That's the number of A intersects B over the number of B. Right? Number of A intersects B over the number of B. The intersection will be 1 and B will be 5. That's 0.2. State whether or not the events A and B are independent. So what we can see is probability A given B is not equals to probability A. So not independent. Because whether B happens or not will has an influence on the probability of A. Therefore, it's not independent. Okay, that's we use the first formula. Okay, we use the first formula. Example 2. A selection of 6 different baby trolleys include 3 with free ring cover, 4 with sunshade and 2 offers both. Let event A will be with a 3 sunshade. Okay, I want a Venn diagram. So event A and event B, I have 2 in the middle, and okay, 3 sunshade. I have 4 with 3 sunshade. Okay, so I have 2 here. B is with 3 ring cover. I have 3 with ring cover. I have 1 here. 5, 6 have 1 outside. And I want to know probability A. Probability A will be 4 on 6, which is 2 over 3. Probability B will be the number of B over the number of total. Three on 6, which is half. Probability intersects A intersects B will be the number of A intersects B over the number of total. That is 2 over 6, which is a third. And state whether or not the events A and B are independent. Because it's already asked you to find those 3 things, and you can obviously see that's using the second formula. Okay, it's using the second formula. But you don't know whether, like, the second formula says intersection equals to A times B. So you need to find the probability A times B first. Probability A times B equals to 2/3 times a half. That equals to 1/3. And then say because probability A intersects B has the same number of probability A times probability B. Okay, they are the same because you just work it out. Okay, you times them together, you work it out, and you say they are same. So A and B are independent. A and B are independent. Okay, that's the use of the second formula. Any questions about those 2 exercises? They are very important. Okay, actually, like, we don't have enough time to cover that in the exam, so that's why the probability questions are really easy in the exam. So if we learn those 2 exercises, we should have harder probability questions. So most of the time we ask things in conditional probability and independent events. Okay, you can see all the VCAR papers, almost every question is asking those 2 things. Okay, so it's quite important. Well, I just want to give you one. Okay, I just want to give you one thing. Let's say we have, well, that's a VCAR question, but I can't clearly remember what is the question. I'll make up that. So I'll say we have a full set. We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's my whole set. And then set A will have 2, 4, 5, 7. And set B will be 1, 2, 3, 4, 5. And ask you whether A and B are independent or not. Okay, whether event A and event B are independent or not. What you should do. Which formula you should actually use in this case? You can use both, but like the first one will be harder. Okay, it will be harder. Like if you want to use the first one, you need to think about the Venn diagram. Well, I just want to ask, what is the A intersects B? Huh? No, it's a set. I'm not asking the probability. 2, 4, 5. Okay, then it's easy. What's the probability A? Half. What's probability B? 5 over 8. What's the probability A intersects B? Are they times together will give you that? No, so not independent. They are not independent. So you will say what's probability A times probability B gives you? 5 over 16. Although it's quite close. Okay, that's 6 over 16, but it's still not. Okay, they are not equivalent. Therefore, they are not independent. So that's how we do those type of questions. I think we can ask in a much harder way. No, it's a multiple choice. Yeah, I remember. It's a multiple choice questions and give you a lot of events. Like five options. And with A is what, B is what, A is what, B is what, and ask you which one is independent. You need more calculations. Okay, you need more calculations. Okay, so have a look at 9H. Okay, well, you don't really need to do anything to 9H. You just need to listen to me to tell some stories. Well, like this is actually the fun part of probability, or let's say this is the part really like doesn't matter what job you do. Like if it's related to probability, you will need simulations. Well, why we need to know this? Because like we won't always have those events. Okay, all the data is given to you. You know everything, and that's so easy to deal with. And it's just pure theory here. So what we need for simulations? So simulation is a sample. Okay, so find solutions to problems where exact solution is difficult to find. So if something like you want to investigate something, but like so hard to get data, we use simulation to find it. So difficult or impossible to find. In order to use simulation to solve a problem, a clear statement of the problems and assumptions must be made. Okay, assumptions must be made. A model must be selected to generate outcomes for a simulation. Possible choices for physical simulation models are coins, dice, and spinners. Random number table, calculators, and computers may also be used. Each trial should be defined and repeated several times, at least 50 times. The result from all the trials should be recorded and summarized appropriately to provide answer of the problems. So, what basically we're trying to do? I think it's better to give your example here. Just have a read of this example. A pizza shop is giving away football cards with each pizza bought. There are 6 different cards available. And a fan decides to continue buying the pizza until he got all the 6 cards. Okay, well, you can keep getting the same cards. Or like say, I already get to 5 cards already, but like the next one will always repeating. It's hard to get the last one. So I don't know how many pizza I need to buy. So how many pizza will need to bought on average to obtain the complete set of the cards? Okay, so this data is hard to collect. You won't really stand in front of the pizza shop and ask the people working out, oh, how many pizza you already buy? Do you have all the cards? And say, no one really interested, maybe not all of them, or very few of them were interested in getting all the cards. Like, I won't bother with that. Well, someone wants to get it. But like, even though I want to know the result, I won't keep buying the pizza. Okay, I won't really go into the shop and keep buying the pizza and know this data. Even though I did this, I can only did it once. I won't try twice. Okay, I only did it once, and it's not a good data. I can't say, oh, this is the average value, because you only did it once. You can't say something average. You need to do 50 times, and it's so hard to get. Okay, so hard to get. So what we will do is, okay, we can use some other tools to help us to think about like a similar situation. Well, I have 6 cards. Okay, I have 6 cards. I can throw a dice and record the number. Okay, 1, 2, 3, 4, 5, 6 represent 6 different cards. Okay, I throw the dice the first time, I get a 1. Throw it the second time, I get a 1 again. Throw it again, get a 4. Okay, and keep throwing until I record down like all the numbers. Okay, 1, 2, 3, 4, 5. Make sure all the 6 numbers appears. And I count how many times I have thrown the dice. And that is how many pizza you need to buy. Does that make sense? Okay, 6 number. I need to keep rolling the dice and until I get all of the 6 number. And I count how many times I have thrown the dice, and that's the number of pizza I need to buy. And I will repeat this for 50 times. Okay, I will repeat this experiment for 50 times. Well, if you think it's too hard to do, you will use your calculator. There's stimulation buttons in your calculator. And you can do, calculator can just doing this step for you and tell you, oh, how many times I need to get all of the 6 numbers. And have a look. Have a look. 5, 2, 5, 2, 2, 2, 3, 3, 1, 2, 6, 3, 5, 4. That is the trials for the first time. Count how many numbers are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I throw it 14 times to get all of the 6 numbers, which means I need to buy 14 pizzas. Okay, I need to buy 14 pizzas. And I will do that another time. And you can see this table here. First time I throw it 14 times, but second time I was lucky. 8 times is enough. Again, I do it again, got 12. Until the last time, that's the 50 times. Okay, the 50 times I get a 9. Okay, I only use 9 times to get all of the 6 numbers. And on average, I want to know the number of pizza I need to buy on average. I just add all of these 50 numbers and divide that by 50. Okay, divide that by 50. And I get approximately 15 pizza I need to buy to get all of these 6 cards. With what? No. There's not really a formula thing. This is more like different case. Well, that's pizza and only have 6 cards. Well, if you have 10 cards, there's different. You can't use dice anymore.
Yeah, but if you're going to probability of rolling, if there's only that, no probability of getting these numbers.
No. This thing is actually what we need. It's not on theory. Like, experimental probability and theoretical probability will be different. Well, in theory, for example, I throw 100 times of the coin. I should get 50 and 50, but I won't. Like 99% of the time, won't. So that's more realistic. Like what I will have, I need to do. Well, if in long term, like really, really long term, it's hard to say. There will be potentially to a number, but like we're not interested in the long term thing. I'm more interested in this time what I go in and I will get. Like most of the customers, what they will have. So this is more realistic. Okay, we really do the experiment and get the data and then do things. Okay, so I don't think we'll get test on those type of questions. Well, you won't have a dice, throw it for 50 times. No, not 50, maybe 1,000 sometimes. Like to get a data, well, you can do that on calculator, but like in methods, it's not really part of the course. Okay, it just needs to make sure you hear the story and have some fun if you want to with your calculator. Okay, so we finished probability.